Oh, hey. Um, for whatever reason, yeah, OBS or Discord or combination of multiple things decided that it was just going to, jump off a cliff. Um, Hooray. I don't understand what the problem is with this, but well, anyway. Ugh, I just did ads. Yeah, thank you. So I don't know what combination of programs I have that just does this occasionally, but Ubuntu just dropped me to the login screen. Everything completely froze up, which sometimes the Wacom tablet just does that by itself. It can do that. But anyway. What is your issue, dude? Not you. I was like, yeah, 5 minutes until ad break. No! I snoozed it for a reason. Oi. So yeah, when we're looking at like any random arc length, we're looking at 2 pi, which is going to be the circumference amount, and then we have our 41.3 degrees divided by 360 degrees, which gets us the proportion amount. So like, right, so that bit's from the circumference, that bit is the proportion of the circle. And as you said, if we look at these two things taken together, it's going to be the proportion of that 2 pi that we end up, again, going around the circle. So we can just say that now we have, as you'd said, a radian measurement. So how many radii are we going to go around the edge of the circle? So here this is 1r, and then we just wrap it going around the edge of the circle to wherever we want to end up, and we say how many radii is that arc going to cover. Now this is much better because that's going to work on no matter how big the circle is or how small the circle is. It's always going to end up working out to be the same amount in the same place. So if we were to draw in this line for this particular angle, and we say, okay, this is going to be our theta for this, it doesn't matter if the circle is here, or here, or here, or, 20 miles out that way, the properties of the angle that we have here are going to be the same. The distances that we have and that we're going to talk about are all proportional to each other. So all of our individual distances are proportional. That's what's going to really matter. If you look at it historically, right, the Babylonians were the ones who created the 360 degrees number system out of this, because their number system was sexagesimal, i.e. base 60. So they had unique symbols for all the numbers 1 through 60, or rather 1 through 59. And once you reach that new 60th symbol, it rolls over into the next space. So if we did like 1, 1, 1, 1, right? This is how many 60s we have. This is how many 1s we have. So their number 1, 1, as we would see it, actually means 61. 31 would be 3 times 60 is 180 plus 1. And in fact, like, let's do, 40 here. Right, so 3 is going to get us 3 60s is 180, plus 40 is going to be 220 in decimal. So actually, if we move on further than this, I mean, pretty much, yeah. But in ancient Babylon, they would have a triangular stylus and a tablet of clay, and their numbers were basically like a whole bunch of tally marks that went like this way and then that way, and they were in boxes of 9 and all this stuff. And they represented ones and well, all the numbers through 59. There's a whole there is a whole study on cuneiform. So if you want to look into any of that, Irving Finkel of the Royal Society I mean, he literally wrote the book on modern cuneiform studies. So, and this is more or less what cuneiform looks like. These are all sorts of characters, meaning all sorts of different things. He's studied it, ridiculous amount, but yeah, and again, this is just the only things that they did with these were they took a tablet of clay and pressed it with a triangular shaped stylus. So, like, anybody could learn how to read and write anything that was here. It was just a matter of, understanding the language. And there were many languages that used cuneiform. The main ones were Akkadian, of course. Where's the timeline? Akkadian, Assyrian, and Babylonian. So, like, those were the three major languages that used this. And they went from the old Akkadian, started in 2300, BC, BCE. So, you know, this is 4,300 years ago compared to today is when the first, like, Akkadian came about. And late Babylonian period started in 539 BCE. So, again, this is 2,500 years ago was when their latest script was, like, standardized. And the Babylonian Empire fell, or at least, well, okay, the Babylonian Empire stopped using cuneiform. Somewhere around there. Harumph. Okay. There we go. Ugh. Of course, they don't list all the numbers just right there. It's probably in the other book, honestly. Okay, I got letters. Or rather, digraphs. Yeah, these are all like common digraphs that you'd see of, you know, various letter types that go together. Yeah, of course it's in the other one. Yeah, if you get the chance, definitely watch some YouTube videos with Irving Finkel, because he's freaking hilarious. He was talking about, or somebody put up a video as part of another video on like how one of his students that he was just treating like he was just doing some class for whoever wanted to take it and learn Assyrian and like maybe help out a little bit, you know, just cause. And one of the ladies who was there ended up, here's the stylus made out of reed. One of the ladies who was there actually ended up decoding something, and it got like a lot of press. And so they interviewed Irving Finkel, they interviewed a whole bunch of other people. Be like, hey, check this out. Like somebody in modern times decoded something that was on this clay tablet. How cool is that? This is almost the same book. This is almost literally the same book. Cool. That means I don't have it. Well, whatever. There we go. Alright, post that. That's the cuneiform numerals. Yeah. And there's a clay tablet that they found, which is like a series of numbers and all this stuff, and they're like, this is a little strange. Like it's like repeated words and something or other, and then they found more with like exactly the same stuff on it, and they're like, oh my god, this is geometry homework. This was assigned to students who were going to become scribes, and they were, you know, forced to learn geometry. It was like, you have 4 squares with 4 circles. What's the proportion of the overall shape that's shaded, or, you know, inside the circles or something like that? I mean, it's just like, wow, okay, that's exactly the same sort of thing that We do, you know, we still do these days. All right. So yeah, with our S, it ends up becoming that we just need theta as an angle in radians times r, the radius of the circle. So now that we've gone on a wild discussion far afield, it's all good. Alright, this thing's going to run ads in a minute, so I'm just going to hit the button now. It'll be 60 seconds. Very much apologize. This should know better, but it doesn't. Their programming needs work. I'll see you in just 60. So I'm still going to be here. Alright, so anyway. Welcome back, everybody. So, like, this was kind of the point that we're getting into with all these students saying, like, if we just want any arc length, we can do that by breaking down the circumference into a certain proportion. And in this particular case, we just say that that proportion can be now worked with 2 pi as part of the angle itself. And we don't need to use degrees. My point here really was that the Babylonian system is effectively arbitrary. Like, why did they use these? Because it's just the powers of 60. The same that we use today, the powers of 10 as our number system. So 10, 100, 1,000, 10,000, 100,000, a million, etc. They were just using the powers of 60, which are 1, 60, 3,600, and then 216,000? I think. 216, 3 zeros, yeah. So 216,000. Which, like, it works, I suppose. It worked just fine. But the other thing is that the Babylonians originally did not have any sort of way to distinguish one number from another number that looks awfully similar. So, for instance, this could often be mistaken as 61, or 3601, or 3660. And it was really only the context that made sense in terms of whether or not it was going to be one of those particular numbers. So you had to be, like, at least sort of smart in order to get it and be like, there's no way that they meant 3660. I'm sure that this means 3601 or 61 or something like that. When we look at the other angles on the unit circle, then we're talking about, okay, well, what are the easy ones? We take the entire circle, we divide it in half. So you've got, if you didn't go anywhere, it's 0. If you went all the way around, it's 2 pi. If you only went halfway, that's pi. If you split it in quarters, that gets us pi over 2 up here, or an extra pi over 2 beyond pi, which is also 2 pi over 2, gets us 3 pi over 2. And in this way, we can actually split all of this stuff up in terms of just basically counting our individual units that we're using to break up the circle, and the so we're just going to count and then use the units that we're breaking up the circle into. So again, if we have just pi's, well, there's 1 pi and there's 2 pi. If we do pi's on 2, that's 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. 4 pi over 2 is 2 pi. And then we could split that again in half. So we end up with pi on 4 here. 2 pi's on 4 is pi on 2. 3 pi's on 4 is over here. 4 pi's on 4 is pi. 5 pi's on 4 is over here. 6 pi's on 4 is down at the bottom. That's 3 pi over 2. 7 pi over 4 is here. And 8 pi over 4 is back to 2 pi again. So this is the intro, right? To just understand where the angles are. Again, I'm going to suggest that you look at the individual, like, where are these angles? And that is one particular unit. Like the first one in the first quadrant is the unit of that particular angle. And then just start counting with those angles as you go higher and higher. All right, and then we could split this into either pi's on 3, which again, we can go 1 pi on 3 to there, 2 pi's on 3 to there. 3 pi's on 3 gets us to pi. 4 pi's on 3 gets us to the bottom here. 5 pi's on 3 gets us over here. And 6 pi's on 3 gets us back to 2 pi. All right. Pi on 6 is half of pi on 3. So 1 pi on 6, 2 pi's on 6, 3 pi's on 6, 4 pi's on 6, 5 pi's on 6. That's the first, or that's the second unique pi on 6, because all the rest of them are just simplifiable. Right, but you can always just count. So this is 1 pi on 6, 2, 3, 4, 5 pi's on 6. Pi on 6 is just a unit, right? It's a specific distance that we use. And then 6 pi on 6 is just pi. 7 pi on 6 is the next one. Again, it doesn't simplify, doesn't reduce. Nothing really reduces, but you understand, right? It doesn't simplify, so 7 pi on 6 is here, 8 pi on 6 is here, 9 pi on 6 is here, 10 pi on 6 is here, 11 pi on 6 is here. Doesn't simplify, so we can write it again. And 12 pi on 6 is here. 2 curbs! Well, it was coined by René Descartes, who wanted to know why these people were wasting their time on such imaginary numbers. And yes, you can actually call them perpendicular numbers. Did you see the Welsh Labs video, or the series of videos? that imaginary numbers are real. Mm-hmm.
If Galaxy...
Nope. Grr. Alright, that's a link to the live playlist. Yeah, but then you'd have to have a doubled P instead of a doubled C. You have to change all the literature. Mm-hmm. No argument here. Alright, so then, Waffle, the other thing that I say is, well, if we also take the angles which are not shown here, but which split this all up into a nice amounts, we also have another set of angles here. Which, like, I don't know if you can tell, but these are just, like, absolutely perfect when you compare them with all the rest of the angles that we have here. Because these are... These are all pi on 12. Now, we don't talk about them immediately upon starting this unit, but... yeah, they do. We do make lines going through, but that's also something that's going to come up in a bit. But our base unit for the entire unit circle is really pi on 12. So if you look at it, you split the circle up into 24 equal pieces, right? Each one of them has an angle of pi on 12. So this is 1 pi on 12, 2 pi's on 12, 3 pi's on 12, 4 pi's on 12, 5 pi's on 12 is the first one that wasn't written already. 6 pi on 12, 7 pi on 12, 8 pi on 12, 9 pi on 12, 10 pi on 12, 11 pi on 12. (12 pi on 12, 13 pi on 12, 14 pi on 12, 15 pi on 12, 16 pi on 12, 17 pi on 12, 18 pi on 12, 19 pi on 12, 20 pi on 12, 21, 22, 23 pi's on 12, not 2.3. And 24 pi's on 12, back to 0. Boo. So our point, our argument against the Babylonian system, i.e. the one that has 3,600 slices to it, it was also, well, we don't really like 3,600 because that's just too large, so we'll go like 60 by 6. So they had a base 60 system, and then they just multiplied it by 6 instead of another 60. And it worked out nicely. 360 was approximately the same number of days in a year, and in fact most calendars back in you know, ancient Babylon 5,000 years ago were approximately 360 days, and then they had like an extra week of partying in order to match everything back up. And especially when the seasons started drifting so far that their calendar was no longer even remotely accurate. Lunar calendars and solar calendars really do not work together. But they were able to figure stuff out eventually. So the argument against our base 60 calendrical system and the degrees and all this other stuff is that it is literally just arbitrary. They said, well, you know what, it's close enough. No, it was, and the party week was not considered part of the calendar because it was not done every single year. It was done whenever it was needed to resync everything. And sometimes they didn't notice for a while because, you know, the weather fluctuations and stuff like that sometimes drift a little bit too. So it wasn't, you know, terribly obvious until they were sowing in the middle of summer and reaping in what should have been the middle of winter. So yeah, the base 60 and therefore 360 degree system is essentially arbitrary. It doesn't matter what number you're picking there. Hydrate and go. And I mean, a lot of stuff back then was kind of guesses until their predictions lined up with reality. Yeah, I mean, essentially you're looking until a certain constellation is in the sky. Right? Most of them were able to figure that out at least. Like, we always put food in the ground when this particular constellation comes up over the horizon at sunset, or, you know, when twilight goes down. So we can see this is the first constellation that creeps up over the horizon. Like, when that happens. And then you're within, you know, a few weeks of the right time. So the radian system is based on the circle itself. And that's why it is not arbitrary, right? Degrees are essentially arbitrary because it's based on the number system that was being used. And then it just happened to line up pretty well with the number of days in a year. So they're like, oh, well, look at that. Whereas here, the radian system is exact. It will always, like, get the exact value, so mathematicians like it a lot more. It is based on the measurements of the circle itself, so we're basing it off of the circumference, and then we're just saying, look, if you just take the circumference and you scale it up or you scale it down, then the relationships between all these distances remains the same. The only thing is that it's going to be proportional. Okay, so now, Waffle, this is the part that you're going to hate. So, not necessarily, but we start taking these things and we say, okay, we've got our lines, we've got our angles. We know that this is going to be pi on 4, pi on 2. And if you need to start from the beginning, feel free to do that, right? You say, okay, I've got 0 and 2 pi. Half of that is pi. Half of that is pi over 2. We go 1 pi over 2, 2 pi over 2, 3 pi over 2. It's down here. All right, pi on 4. That's 1 pi on 4. 2 pi's on 4. 3 pi's on 4. 4 pi's on 4. 5 pi's on 4. Nope, 4. 6 pi on 4. 7 pi on 4. And 8 pi on 4 just to make sure that that works right. Yes. So the point that we're looking at was that we were taking this initial side here and saying we're going to create an arc that goes up like this, whether that be here in the center of the circle or way out on the edge of the circle going along the circumference. Take your pick, right? I mean... Right, so we take our theta, which we'll just call whatever angle we want. In this case, we'll make it pi on 4. And we say from here, we can drop an altitude to create a right triangle. Now, why do we do this? Well, in the modern era, we like to use coordinate systems with our geometric systems. This is algebraic geometry. Right? We like using geometry and algebra together because it gives a kind of solid foundation for all of this stuff. So, what does this mean? Well, we've done this since Algebra 1. It means that this distance here is going to be x, and this distance here is going to be y. What have we just created? Hey, look at that. It's a right triangle. What kind of right triangle? Well, it's pi over 4 as our angle, which is 45 degrees. If you know how to trade them back and forth, it makes it pretty easy. So it's a 45-degree angle. What do we know about 45-degree angles when there's a right angle in the triangle? Not an idle question. Go for it. Right, this is an isosceles right triangle. It's perfect. That's great. That means that this is the same as that, and that this is the same as that. So now we've got our theta pi over 4, 45 degrees is also up there, and our side lengths are going to have to be the same because it's an isosceles right triangle. Okay, well, this is how we do the algebra for this. And we can get this for all of the easy angles. So here, we're going to mark this particular point. We have a radius of 1. That's 1, 0. Way up here, this is going to be 0, 1. I'll get back to the other one in just a sec. Negative 1, 0. And 0, -1. Right, we got our 4 orthogonal points that do our standard axis points there. And then those are along the outside of the circle. So any particular point, x, y, along the circle is going to have that same relationship that we know from earlier. I'm not going to say it right now, but we'll get there. But this particular one that has a 45, 45, 90, we know is an isosceles right triangle, so therefore the side lengths have to be the same. And if the side lengths have to be the same, what else do we know? Well, we said here our radius, anywhere we want to go on the circle, whether it's up, down, left, right, or diagonal in any direction, right? Literally any direction we want to go, our radius is always just going to be 1 for this unit circle. So this radius is also 1. Alright, what's the relationship between the three sides? Forgot we needed it immediately. Psh. Right? So if you want to algebraically draw a circle, then the equation you need is x squared plus y squared equals r squared, as long as that is centered around the origin with radius r. So here we couple this together. And now we say, oh look, here's a right triangle. Its three sides have to also exhibit this relationship. So x was just x, y is also x for this isosceles triangle, and our radius was 1. So now we've got 2 x squareds is going to be equal to 1. 1 squared is 1. Alright, this is x squared is a half, and so therefore the absolute value of x is going to be equal to 1/4. Nope, that's not right. Jeez. What am I doing? Man. Square root of 1/2. There we go. So in this, we could do square root of top over square root of bottom, 1 over the square root of 2, or root 2 over 2 if you prefer to rationalize. I don't really care for me, but everybody else needs to know how exactly that works. What does that mean? Well, that means that all of our values, x's and y's, because the x's and the y's have to be the same, have to either be a positive or a negative root 2 over 2 or 1 over the square root of 2. The square root of 2 is approximately 1.414, and so square root of 2 over 2 is going to be approximately 0.707. That's supposed to be there. Or at least to be the same as the other one. The other one might also be awfully just wrong. So this gives us x values and y values of approximately 0.707, which if you wanted to go like, hey, where is that along this actual vertical distance? This is about half. That's about 3/4. So 0.7, yeah, it's about there. And then with my wobbliness, this is still going to be off by a bit, but, you know, looks pretty good. Right, we go halfway here, looks to be about there. Halfway again, looks to be pretty close. So it's actually just before that, but whatever, it's fine. Yeah, memorization is awful. I hate it. So my way of memorizing stuff is just familiarity. You have to just do it over and over and over again. And the more you see these numbers, you'll just recognize it. I was doing something where I ended up getting 1 plus the square root of 3. And like through trig, I've been using the square root of 3 over 2 all the time. So I know 0.866, bunch of decimals, whatever, is going to be root 3 over 2. And I ended up seeing a number that was 1 plus the square root of 3. So it was about 2.73, something like that. And I was like, I've seen that number before. I know what that is. Give me a sec. What is this? Yep, that's also another way, right? Do an estimation. 1.5 times 1.5. Well, 3 halves times 3 halves is going to be 9/4, just slightly bigger than what you needed. 9/4 is like 2 something. So, yeah, it's 2.25. Oh. Taking the square root of 2.25. Yeah. So the square root of 2.25 is 1.5. And you know that 2 is lower than 2.25, so therefore the square root of 2 is lower than 1.5. Okay, thank you. I got it now. It's sort of backwards. Yeah. Yep. Yeah, if you know your perfect squares, like, again, if you know that 15 squared is 225, then 1.5 squared, that's 2 decimal places back, is 2.25. So again, if you just see patterns of different numbers, even if they're in a slightly different context, like, there are rules, right? You can use any of the rules you want to modify what you see in front of you to change it ever so slightly into something just a little bit different. And if it's convenient, go for it. Right? So this means that all of these, all I have to do is look at what quadrant am I in, and what does that mean for these particular points. So this is the square root of 2 over 2, comma, the square root of 2 over 2. Cool. In quadrant 4, since I already wrote it, this is to the right, so therefore x's are positive, and it is down, therefore y's are negative. So positive x, negative y. But it's the same distances, right? This saves the memorization bit so much. The first quadrant, you just take what's in the first quadrant and mirror it into all the other quadrants. And all you have to do is remember, what are my x's and what are my y's in terms of just their signs, right? Negatives that way, positives that way. Okay, there's your x's. Your y's, you got positives that way, negatives that way. Great. You don't have to think about it. You don't have to memorize it. Right? This is going to be a negative x, negative root 2 over 2, comma, positive y because it's up, root 2 over 2. 5/4, this is going to be negative on both because we're both left and down. Both of our variables here are negative. If you got sent back in time, probably the most valuable tool I could figure out how to create is the slide rule. Yeah. Not embarrassingly. You know what? I don't know where my slide rules are. I started a collection of them. I found a bunch on eBay. I was like, I want one of like multiple different kinds. And so I just pulled a whole bunch. I was like, let's do it. So I collected yeah, I collected a few different ones that were, you know, different enough from each other that it was kind of interesting. You know, all the old engineers were selling theirs when they retired, essentially, on eBay. Go back in time and invent the printing press. All right, so then what do we do for thirds? You know, pi's on 3. Well, if we were to go in and say I needed to create something that was about a third. That is not a third. It's at least closer. Tiny bit lower. Oh, right. No, I know what I need to do here. I need to... I got the stylus the wrong way around. Cool. If I were to cut this in half, that's about there. Give or take, nah, that's a bit higher. Yeah, it's pretty close. So, give or take, good enough. Oops. Yeah, okay. So if I draw a line here, this is going to get us our pi on 6, which again could be repeated in around the whole circle multiple times. But if we just leave it here for now, and we also create an exact replica of it going in the opposite direction, right, this pi on 6 and this pi on 6, although in this case it's going to be negative, i.e. going in the other direction, these are still equal angles, and they have a value of 30 degrees each. What have we just built? Silver, I think you mean extremely hot. Good evening and welcome back on, Ann. I gotta tell you, people around here melt when it hits 30 degrees. Alright, so first of all, this creates two right angles here to make that right triangle, or those two right triangles. But it is, in fact, 1/6 of a hexagon, which is what other kind of shape? Ranking? Right, so if this is 30 and this is 90, then how much is that one? And then how much is that one? And therefore, what shape is this? $2D regular simplex. Thank you so much. Right, this is all 60 degrees, and therefore we typically would call that an equilateral or equiangular triangle. And so when you get this equilateral triangle, that means that this and this all have to be equilateral, right? Equidistant. So here, this means that, again, all of our radii were 1, and these are just going to be half the radii. Right, we could do this whole side angle side nonsense or whatever, but we don't need to. It's fine. Angle side, whatever. You could go either way. So this means that we've got our y distances now. Our y distance is going to be a half up top and negative a half down bottom. So then what's the x distance? We don't have that yet. So we're going to do the same thing that we did with the 45, 45, 90 triangle. We're going to come in here and say, okay, this is going to be x squared plus parentheses a half squared is going to be equal to our 1 squared, the radius. So this is a quarter plus x squared is going to be equal to 1. So x squared is going to be 3/4. And so the absolute value of x is going to be root 3 over root 3 over root 4, which is just 2. Yep, build equilateral triangles, right? Try to make the simplest shapes that you can possibly think of in these in these circles. Don't go off and try to find some crazy angle. Find the easiest ones you possibly can. So here, our x distance is going to be root 3 over 2, whether that's positive or negative. And all you have to do is remember context, right? Positive that way, negative that way. That's it. So we've got here root 3 over 2 comma 1/2, root 3 over 2 comma negative 1/2, and then we just go to the other side. Yeah. But again, this is like, you wouldn't need to like memorize it, because now you just like, oh, well, I can just derive them. So negative root 3 over 2 comma negative 1/2, and negative root 3 over 2 comma positive 1/2. Again, this one is going to be 5 pi over 6, and this one's going to be 7 pi over 6. This one is 11 pi over 6, or also negative pi over 6. We talked about that. Here, those are equivalent. And then this one's pi over 6 up there. All right, so how much work do we have to do in order to get the pi's on 3? Yep. Awesome. I thought I was on the line tool. I was not. A butt ton of work. Really? Why? In fact, let's not do this one. Let's just move it over the other way. Yeah, just because it sounds right? Yeah. Right? What angle is this? These are all of our pi's on 3, right? So this is the same as that angle here. Not this one here, this one here. So this internal angle to the triangle. So again, this is pi on 3 in the default position, right? It's just a 60-degree angle, and it is a 60-degree angle, which means that this one is which means that this one is 30, which, hey, we've done this before. We can make another 30-degree angle here with a 60-degree angle here with a 90-degree angle there. And where are we? Right? What are these distances? Shock and awe. This is not surprising here. This is still 1 because it's a radius. This is 1 and this is 1 because it's a radius. Oh, look, it's an equilateral triangle. That means that here, this distance is a half. This distance is 1, and this distance here is root 3 over 2, but in the negative direction. right? So what have we done? We just took our triangle that was like this and we flipped it like that, right? From being sideways, we flipped it to being vertical. Nothing actually changed. Oh, you never know. Give it time. So here, right, this is going to get us a... Oh, look, our x distance is a half, but now it's in the negative direction, so this is negative a half. Comma, and then now we've got the long distance, again in the negative direction, root 3 over 2. And then we go up top, and we say that's going to be the same stuff, it's just in a different quadrant, so we just have to shift the signs. So this is going to be negative a half by positive root 3 over 2. This is going to be positive a half by positive root 3 over 2. Send your teacher on in. I'd love to discuss stuff. 1/2 by negative root 3 over 2. So, like, that's what you get. Each of these individual places, that's all you need to do. You say, hey, I know these special triangles, and now I'm going to fit them into every different possible orientation that I can in order to say, here's some new stuff. Here's some new angles. Here's some new side lengths. So therefore we get new coordinates. Now, unfortunately, that's it, right? We've now got the coordinates for all of the major multiples of pi, multiples of pi over 2, multiples of pi over 4, both directions, and now the multiples of pi over 6 and pi over 3. We're still missing these pi's on 12, but that's going to have to come later. There's no nice way to do 15-degree angles. We haven't done that, right? We could try like breaking it up into smaller bits, but it's just not going to work for us. So we're going to have to wait on 15-degree angles for some other time. But, right, here's the thing. Here's the other thing. Here's one of the other things. So, what we have now is a series of inputs which is going to be the amount that we have gone around this circle. So this is going to be our angle in radians, because I said so. Right? And we can have our output. Our outputs for these particular functions that we're finding here could be coordinates, could be ratios, right? They could be, no, that's pretty much it. Right, your arc length, your angle is what we're inputting. That's going to be our independent variable, and either coordinates or ratios can be our outputs or dependent variables. So yes, this is a function setup. And we're only going to do one at a time, right? We don't want to go completely overboard on this stuff. It's fine. So, the first one we're going to do is we're going to look at what happens when we start looking at some random angle. Again, we'll just call it theta. We have our R here. and we have our x distance here, and we have our y distance here. So there's a number of different ways to have the to show off the relationship that exists within all of this stuff. You've probably heard of a couple of things. So, delving way back into your delving way back into your pre-trigonometric type stuff, you've probably dealt with some trigonometric functions, probably in a geometry class. Right? Now I'm going to urge you to probably forget the that particular phrase, just because it's memorization. It doesn't really help all that much. But even if you were to somehow forget all of the names, right? You're not going to forget all the names. It's fine. There's an easy way that you could just double check, right? Which one am I thinking of? Is it the vertical or is it the horizontal stuff? So what we could do here is we look at the sine function. The sine, or sinus, coming from Latin, is going to be the ratio between vertical, or the side opposite the angle, and radial sides. So in our diagram, right, f of theta is going to input our theta, and then it's going to output the ratio between our vertical, which we've labeled y, and radial, which we've labeled r. Now, it does not matter where that is. It is still going to be on a circular path as we're going around the origin, as we increase the value of theta. It's still always going to be in that same it's still always going to be in that same ratio. And we're still going to follow the exact same path. So again, always we have x squared plus y squared equals r squared. So when we look at this, we're going to say, okay, let's take a look at the unit circle that we had up there. It says that f of theta, sine of theta, is going to be equal to just the y coordinates of any individual point on the unit circle. So we're looking at just what are the vertical values that we have. So we start with our theta, and then we say, okay, what is y? Which again is going to be equal to the sine of theta on a unit circle. So oftentimes what we do is we just pick the important values that we had up there. So 0, pi on 6, pi on 4, pi on 3, pi on 2, 2 pi on 3, 3 pi on 4, 5 pi on 6. All right, and then we'll keep going as necessary. So at 0, what is our vertical value? At theta being 0, what's our vertical value? Yeah, it's just 0. We haven't moved up or down at all. We're just off to the right. We are exactly along the x-axis. So yeah, that's 0. Now, the other thing that you can do here is find the easy values. So don't necessarily go in order, because who cares? It doesn't matter if you go in order. Find the easy values. What do you know is also going to happen? Right? We get a 0 at pi because that's just over there. It's along the x-axis again. What else? Right? So easy values. We know that it reaches a peak at pi on 2. Why is it 1? Right? The y value is the radius. So they match. It's going to be y over r is equivalent to each other. It doesn't even matter what circle you have, right? The sine value here, the y divided by the radius is going to be 1 because they're the same thing. All right, where else? Yeah, 3 pi over 2 is also radius this time. So the y value and the radius value are going to divide out and make 1 because they're the same number. But what's different? Yeah. Right? 3 pi over 2 is going to be negative 1 because here the y value is negative. The radius is always positive. It's just a constant 1 or whatever it ends up being. Because again, it doesn't actually matter whether r is 1 or not. R could be 50 and the y value is going to be scaled up just by a factor of 50 off of what the sine function is going to get us. The sine function always comes out to be these same values by default. Right? 2 pi? Yeah, also 0. So now at this point, we just kind of fill in the numbers that are up there that we got. So pi on 4 is going to be root 2 over 2. 3 pi on 4 is also going to be root 2 over 2 because this is, again, y values. We're currently up. 5 pi on 4 is down, so it's negative 2 over 2. And 7 pi on 4 is down, so it's negative 2 over root 2 over 2. Our pi on 6s are low, right? These are 30-degree angles. They're shallow. So these are going to be the short sides of our 30, 60, 90 triangles, which were half. In 7 pi over 6 and 11 pi over 6, they're negative. So again, negative a half. And on pi on 3, these are the long sides. So our vertical sides are the long sides. So that's root 3 over 2 for each of these things. Okay, and negative root 3 on 2 for both of these. Okay, I'm going to go for a 1-minute break here to get the pre-rolls knocked off, and we'll come back in 60 seconds and work more on this. I'll just draw the axes and stuff. Be right back. Probably 15 minutes. I don't know that you want to do that right now, but all right. So here our axes are going to be theta going across and y over r going up and down. So again, we could call it f and just call it the sine function or whatever, but nonetheless, the point is we're trying to make this the ratio between the vertical and radial sides. So we'll do this. We'll max out at 1 and minimum going to be negative 1. We go all the way out to 2 pi over here, and in the negative direction we'll figure that out in a minute. But mostly we have numbers here, right, which are our theta values from 0 to 2 pi, and we have vertical values, y over r, between negative 1 and positive 1. Here's my recommendation. 1. Find your origin point. Well, in this particular case, 0, 0 is part of our function. Great, we'll keep it. 2. Find the end point. This point, it is 2 pi comma 0. 3rd, go halfway. That's pi. It's also a 0. Go halfway again. This is pi over 2, and this is 3 pi over 2, which are respectively 1 and negative 1. Go halfway again. These are odd pi's on 4. So 1, 3, 5, and 7 pi's on 4. Their values are root 2 over 2, which we already discussed, is 0.707, which is, roughly speaking, just under 3/4. So this is going to be roughly about here. This one's going to be roughly about here. And they're not symmetric either. I messed up some of the distancing. It's fine. Nobody's going to care. Here we go halfway, and then halfway again. And again, we go just above that. Here and here. What do you think? Nah. And this is the other thing, right? It takes time. It takes practice. If you've done this a bunch, then it'll take practically no time at all. And you can get this in less than a minute. That includes doing all sorts of crazy function transformations on it, because I have also worked out a way to graph function transformations that make this much nicer. We'll talk about that some other time. In addition, if you want to graph the other points, the pi over 6 and pi over 3 are 1/3 the distance between your pi's on 4 and pi's on 2. Or whole pi's or whatever. So if we mark 1/3 of the way in either direction, again, this one's going to be pi on 6, this one's pi on 3. Our values for this, the pi's on 6 are 1/2, so we already have a point for that. Pi on 3 was 0.866, which is pretty close to 7/8. Bit under it, again, but pretty close to 7/8. So again, if we do this about 1/3 of the way between the quarters and our major either halves or wholes, we can mark those points again. Again, it's off by a bit, but whatever, it's fine. If your teacher is like super strict about stuff, you know, maybe you need to be a little more careful, but honestly... Oop, no. A little bit lower. These should not be collinear, is another thing. If they are appearing to be collinear, as in making a straight line, that is a problem. Furthermore, right, these should be essentially grouped. So you're going to have like these three and these three are going to be closer together than they are to either of your major points. Alright, so with more points, what do? Well, we just kind of graph it like an artist. Make some individual lines as you're trying to make a rough drawing. If you're trying to make a more formal drawing, you know, need to get a little bit better at it. It's fine. You'll get it eventually. And eventually, these should be perfectly symmetric, both up and down. I would recommend using graph paper. Yep, I say that too. Yep, if the dot is slightly off, just make a bigger dot. Nobody's going to care. Perfect. Look at that. Right? And then what do? Well, if you want to continue this, you could say, all right, we got all these here. Could be copy-pasted. Right there. And we're off by quite a lot. Ooh. That should be there. There we go. Perfect. Nobody saw anything. Right, so this is going to be negative pi over 2 here. And similarly, if we want to do another do another one in the right direction. That could be there. Yep, perfect. Woo! Something like that. Hey, thank you, Waffle Walrus. No. So there is not a way to get the sine function from using any polynomials directly. You would need to. This is the fun part, right? So you would need to go in and say, I'm going to take a series of polynomials, and it will be an infinite series of polynomials. And then you can approximate any function you want. So in theory, you could estimate any particular interval using any particular degree of a polynomial, right? You could, but it wouldn't be a great one because at its heart, sine functions are circular, right? It's not like don't make a circle either. Don't make like, oh, here's a semicircle and another semicircle. It doesn't work like that. So the point of all of our like functions that we're going to be dealing with, right? Your sine function is going to be based on the vertical value that you're getting as you're moving around the circle. So as you keep moving around the circle, all we're doing is we're measuring how much this is going up or down based on its position like this. This is harder to do than you think. Right? Whereas in a polynomial, what we're doing is we're having this like linear acceleration, or, well, no, constant acceleration toward a particular direction. So in theory, yeah, sure, you could do it over a small interval. In practice, it's not really that good because it's a fundamentally different kind of curve than circles, and polynomials are fundamentally different kinds of curves. Okay, well, this also means that we could go through and do exactly the same thing but now, instead of our y values, right, what if we did the other trig function that you might be thinking of? So what if we were to look at the ratio between our x and our r, rather than y and r? It is. But here's the thing, right? Again, I don't really want you to think of it in terms of, oh, it's just x values. What we want to do is show you why they are so named, right? X's are going to be your cosine thetas on the unit circle. R equals 1. Or else you could say, okay, x over r, our ratio, is going to be the cosine of theta. Yeah, don't worry about that just yet. So, like, it just being a phase shift is all wonderful and stuff. But you really have to understand, like, the nature of phase shift in the first place. Right, so we go like this. We say, okay, we've got our first quadrant. We've got our particular angle that we're looking at, which is just going to be some random angle, right? It's not particularly anything. This is going to drop down. We still have our x distance here and our y distance here. We still have our right angle. We still have our theta, which is going to be that, and we still have our r. So, here's the thing, right? The ratio x over r is still a sine ratio. But it is a sine ratio of what? If I'm not being clear, that's fine. So the sine of theta is going to be y over r. Almost. So we'll just label it alpha, first of all. But more importantly, right, what is alpha? Alpha has what relationship to theta? Yes. Right, because we have this 90-degree angle already in here, it's taking away 90 degrees out of that available 180. So then all that's left is 90 minus theta to get us that alpha.
Raiding party!
It is the complement, yes. Good evening, readers. Hey, Don. How's everybody doing? My name is Obi-Wan Pez, and this is N Simplex Pachinko. Anybody who doesn't know me, I do mathy type stuff here. Don also does mathy type stuff here, though usually on his own place. What kind of math were you all getting up to tonight? So, Waffle, here's the thing, right? If you look at this, the sine of alpha is x over r, which is our ratio that we want to get. So, the sine of alpha is the sine of the complement of theta, or the complementary sine of theta. Jed, you are free to take the theta if you wish. Right? Words have meanings. And if your teacher is not teaching you the meanings... Oh, complimentary, yes. Jed, did you see that updated family vacation commercial? We speak English, I can't assume anything. Fifi. So Chevy Chase as Clark Griswold is looking ever the grizzled retiree at this point, with his retired wife standing at the concierge counter at the hotel, and he goes, "Well, I thought this water was complimentary." And the concierge says, "Yes, sir, it complements the room. It is not complimentary." And so he's looking at the bill and just like... Phi? Yeah. Yeah. So with this, our x over r is the complementary sign of theta, and so we say it's the cosine of theta. So if you're ever like really confused about what's what, all you need to really remember is the sine function. Because you're saying, I want the sine of this particular angle, so therefore it's the opposite over the hypotenuse. Okay, it's y over r. Then if we say, I want the cosine, what is that? That's the complementary sign, so it's the sine of the other angle. So here, if we do that, right, we already got a whole bunch of this stuff from up above, but if we're looking at it in terms of our x values, because again, r is 1 on the unit circle, so we don't even need to worry about it. Right, at 0, our x value is all the way over there. It's 1. And then that means that on the opposite side of the circle, we're going to get a negative 1 going that way. So that's at pi. And at 2 pi, we're going to get another positive 1 because that has to be back around this way again. All right, same thing with our pi over 2 and 3 pi over 2. In this case, our horizontal value is 0. Because now, again, we're going straight up and down. We're not going side to side at all. So pi over 2 and 3 pi over 2 are 0 for our cosine. We're looking at the x values, the x distances. So then where does that leave us? Well, at pi over 4, again, we're looking at horizontal values. Pi over 4 is always the same for x's and y's. It's just straight 45-degree angles. So it's either going to be root 2 over 2 or negative root 2 over 2. If you're between a 1 and a 0, take a guess which one you want, right? If you're between a 0 and a negative 1, which one do you want? Okay, and the more truthful way to find that is, what direction am I going in from the origin to get to all these points, right? To get to 5 pi over 4, that's in the third quadrant. I'm going left, therefore my x values are negative. I'm going to 7 pi over 4, that's in the fourth quadrant. My x values are positive. Okay, and then we've got our pi's on 3 and pi's on 6. Again, same deal. Our x values for pi over 6, that's way over here and then up a bit. So what does that mean? Again, we're pulling up just a bit. Our horizontal distance isn't really changing all that much. And again, it needs to be between 1 and root 2 over 2. So root 3 over 2 is that longer side for the pi over 6. Pi over 3, it's much steeper, so it's a shorter x value. That's going to be our 1/2. 2 pi over 3, we're on this side now. That's negative. Again, it's short, and then it lengthens out. So negative root 3 over 2 for 5 pi over 6. 7 pi over 6, it's the same stuff. It's a long x distance, and then it shortens back down, so negative 1/2 at 4 pi over 3. 5 pi over 3 is going to be a positive half, and 11 pi over 6 is going to be a positive root 3 over 2. Okay, so now that we've got all this, we do the same thing again. We say, okay, what's our graph going to look like? Okay, so we go up here, this is going to be a 1. We go down here, this is going to be a negative 1. We go all the way out here, this is going to be a 2 pi. And then we split this in half and go with pi. Split this in half, go with pi over 2 and 3 pi over 2. Go with pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. And then we go with, again, we start at the origin point. The origin point here is still 0, 0, but it's not part of our graph. So I leave that as open. There's a reason. And again, we'll talk about it when we do function transformation. Okay, at pi over 2. This is going to get us 0. You know what? I don't do that yet. Sorry. The way that I do this is that we start at the initial point. Our initial point is at 0, 1. Right? 0 degrees, 0 radians, comma, 1 for our x value, our horizontal value. Then we go all the way to the end of the period, which is 2 pi. That also has a value of 1. Okay, then we go to the middle of that. And this one's going to be at pi, comma, negative 1. We already wrote that. Okay, and then halfway in between each of those is going to be pi over 2, which is 0, and 3 pi over 2, which is also 0. Halfway between those, we get our quarter points, which are at pi's on 4. And this is, again, half, 3/4, not quite 3/4. Going down, half, 3/4, not quite 3/4 the way. This one up here. And again, if we want to do more points to get a more accurate graph, around the pi's on 4, we go about 1/3 of the way. Well, no, we do go 1/3 of the way from those pi's on 4 to the next major multiple of pi. And we mark those out, and then we say, okay, these are also going to be, again, 0.866 is roughly 7/8, a little bit under. This one's going to get us, again, about a half. It is a half, sorry. Jeez. Pi over 3 is going to get us a half. 2 pi over 3 is going to get us negative a half. Right? And then 5 pi on 6 is going to be pretty close to negative 7/8. And then we do the same on the other side. Give or take. Look, it's not perfect. It's not exact science. Right? That's what we got. So it's going to look something like this. Again, we're going to get pieces that are either copied into the right or left direction from here, but this is our first period. Minimums of one function match to the maxes of the other. So not quite, at least not in this case. If you were to overlay our g of theta equals cosine of theta here with our f of theta equals sine of theta in blue, we'd end up with points that go here, here. We'd go through pi on 4 at the same place. Pi is 0. This one is here. This one also here. That is here. That one is here, and that one is here. So we'd end up with something that looks like that. So 100% correct. Silver said, well, this is just kind of a shifted version of the other. And that's true. But usually I don't want to bring this up immediately just because we didn't talk about function transformation. We have not talked about function transformation yet. And also, my students need to see like the basics of these particular functions before they start going on to talk about like the transformations of these functions. But here's the thing, right? Ayo. If we're talking about the complementary sine of theta, right? This means that the cosine of theta is going to be equal to the sine of alpha, which is the sine of pi over 2 minus alpha. Which, given the way that function transformations work, right, this is going to be the sine of negative parentheses alpha minus pi over 2. The way that function transformations work, we're going to take our other color. Going to take our other color. Cosine of theta, our G in the sort of orangey color over there. Right? We're going to take our sine function, which is in blue, the original one, and we are going to... What we're going to do is we're going to take our sine function and we're going to reverse it horizontally around x equals 0. So about where the origin is, it's going to flip horizontally. So instead of as it stands right now, right, what that would look like is that would end up going up here first, like that. So this is the sine of negative theta. And then what do we do? Well, that would need to be shifted to the right, alpha minus pi over 2, shift it to the right. Oh, sorry, that should be theta here and here. Right, because we changed alpha to become pi over 2 minus alpha. All right, pi over 2 minus theta. There we go. Right, and shift it to the right, pi over 2. Well, this was at pi over 2. Negative pi over 2. So now it's going to get shifted to the right to 0. So now our maximum is going to be at 0, comma 1. All right, and this works for all co-functions, and very intentionally, right? Because our co-function is saying what happens if we take the same function, but it's on the complementary angle to the one that we're concentrating on. All right, I'm going to get rid of this so it's not confusing. I'll leave that bit. But then, right, what about tangents? Well, if we're looking at just a regular, unit circle type thing, anybody who hasn't seen this yet, you're in for a real treat. You're about to have your mind absolutely shattered. I know I'm ordering big here, but... Right, so we're going to go like this. we're going to say that this is our standard, right? The point here, x comma y, which gets us these thingies here. We got x here, we got y here, we got theta there. Theta there. And then r there. Alright, you know what I want you to do? Super easy. Draw a tangent to that circle at that point, x comma y. There's several ways that you can actually like draw this in to make it work. I'll show you both. So if we draw in the tangent line, that's here, give or take, right? It's going to be off by a little bit just because. But we do... Oh, don't do that. Nope. Don't curve it. Okay. Now there's a special property that we do know with tangents and circles. And that is that their tangents and radii need to be at right angles. That's not the mind-shattering bit. We're not there yet. Don't worry. Nope, nope. Oh, good. Okay, so go like this. Close enough. Now we'll extend the tangent and the x-axis out as far as you want to go, right? As far as we need to go. So here... this is going to be... now, to be fair, it's r times because it's going to get scaled up to be whatever r is. But it's r times the tangent of theta. When I was dealing with a bunch of my students, I was like, okay, fine, this is just the distance. Don't even call it anything in particular. We could just have it be the distance and just use d as the abbreviation there. Then what we do is we look at the other parts of the triangle that we have. We have r here, which is going to be the short leg of the tangent triangle. Right? We've got this big triangle here. And we've got this little triangle here. They both share a theta. They both have a right angle. Therefore, they both have an alpha, which has to be the same amount. This means that these three angles are the same as each other. Therefore, these two triangles are the same shape as each other. Identical, 100%. They are the same shape. They're just different sizes. So that means that all of our side lengths have to be put in proportion to each other. So the short side of the two triangles are x and r. Short to big, right? So the short side of the short triangle is x. The short side of the big triangle is r. Okay? Then the thing we want is this d or the r tangent theta, whatever we got. And that is the long leg of the triangle. And that is on the bottom here. And then up top, we've got a y. So that is the long leg of the short triangle. So we're trying to find out what d is. All right, flip them over, move them around, however you're going to do this. Multiply d to the left and multiply your x over r, or divide your x over r to the other side. Whatever you got. So our d here is going to be equal to, this is y times r over x. D we already said was r tangent of theta is y r over x. So we can get rid of your r's, and the tangent of theta is going to be y over x.
So am I. The computer that we have running our news from time to time took off and went wild. So what we're going to do is start over from the
Okay, so for this one, we're not going to use y, we're not going to use x, at least not directly. We're going to use the ratio between them. Okay, and if we use the ratio between them, that's going to get us all sorts of different values. Hey, Don, here's the challenge. Do that for all the rest of the trig functions. Right? Draw it out using diagrams, using this diagram. Alright, the other way to do it is if we were to draw our tangent not as the tangent line to this thing, but rather we extend out this side here as far as we need to, and then we draw a tangent line to there we go. And then we all right, then we draw a tangent line to the circle, damn, vertically. That's close enough, you know. It's fine. Then we draw a tangent line to the circle vertically. This distance is also our tangent theta. Now, it probably doesn't look like that because this is, you know, off by quite a bit, but right, the distance here is also r, and this is also a right triangle because your radii and your tangents have to be at right angles to each other. Right, and this is also theta because that's a vertical angle from the other side. Right, and you could draw in your original triangle here if you wanted to as well. Right, so you got your x there, you got your y there, you got your right angle there. This is just one of those nested similar triangles. So, similar triangles, right? This is geometry stuff. This is going back to, like, I don't know, what, 10th grade? Depending on where you hit geometry. Okay, so there's kind of two ways to go about this. One is you're just looking at this in terms of just numerical y over x. That's it. Alright, it's going to take you a minute to figure stuff out. That's fine. The other way to do this is you look at y over x and you say, that looks familiar. Why does that look familiar? And it's not trig. This is working off of 2 points. 0, 0. Oh, man. Waffle. Bingo. 2 points. 0, 0, and xy. And if we were to subtract, because y minus 0 is just y and x minus 0 is just x, this is the slope of our terminal side. So the terminal side is that line that goes right, that is the radius, right? It's the slope of the radius, or the slope of the terminal side of your angle. Whichever way you want to go for it. You beat me to it, awesome! Right? And this means that we now have a physical measurement. Right? We now have a physical distance measurement that tells us the slope of this particular line. This one is going to be positive, and if we were to flip it under here, it would be negative. It's kind of hard to, like, specifically describe if we're using just that, but yeah. Kind of has to do with like which side you're on and a couple of other factors, but the main point is, right, it's the slope of the terminal side. So where's the slope going to be positive? Well, it's anywhere it's going in this direction, so that's quadrant 1 and quadrant 3 immediately. And look at it, right? What's the slope here? I don't know, it's like 1.52. What's the slope here? So I will oftentimes either just put like M terminal or something like that. Yep, it is the slope of the line containing your radius, or the terminal side of your angle. Which means slope, right, going across is going to be 0. So that's at 0, that's at pi, and that's at 2 pi. Yeah, sorry. When you start, so I usually say, you know, in terms of geometry, Euclid, the guy who did Euclid's Elements, which is the most printed book apart from the Bible, which may not quite be true anymore, but this also has the fewest versions, so this might win. So, in terms of geometry, the way that Euclid started out was he started out with a bunch of definitions and then said, here are the basic things that we are allowed to do. So Euclidean geometry started out with, like, what is a point, what is a line, etc. And then said, okay, you are allowed to just draw points anywhere you want. You are allowed to take 2 points and connect them. And in his day, lines actually... No, that's wrong. Lines were finite. We use the term line segment now, but those were considered lines back in his day. And then he said, if you have a line and another point that is not on that line, you can draw in a second line, and then between those two lines is an angle. Now, what we have done, mostly thanks to René Descartes, again, the guy who was saying that, why are these people wasting their time with such imaginary numbers, said, okay, if we fit our angles, lines, all this geometry stuff to a coordinate plane, then we end up getting this algebra which mixes with the geometry. So he decided that the best way to do a lot of this stuff is to, first of all, have your coordinate plane. Secondly, fit this in somewhere. So, one, right, fit your initial side of the angle onto the positive side of the x-axis. It's just basically a convention that we do this. It could be anywhere, but this is the one that we've said, look, we're going to do all this communication. This is probably the best place to put it. Right? And then the terminal side is where the angle will terminate, where it ends. And we also have a direction. So we're going to intentionally open counterclockwise into what we call the first quadrant, then into the second quadrant, then into the third quadrant, then into the fourth quadrant. So we're always going to move in that particular direction, unless we want to talk about negative angles, and we'll go backwards. So in terms of a tangent, in terms of the slope, now we can look at this and say, well, anytime that we go the same distance in the x and y directions, we're going to get 1s or negative 1s. And so that is our pi's on 4. In our first and fourth quadrants, they are positive because they are sloped upward. Or you could think of it as positive divided by positive, negative divided by negative. So those are going to be positive, right? The ratios are positive. And the way that I usually think about positives and negatives when you're talking ratios is, are the signs the same or are they different? In the case of pi over 4 and 7 pi over 4, our coordinates on those points are of the same sign. So they're either both positive or both negative. And when you put them in ratio, that ratio is positive. Okay, then that means that pi over 2 and 3 pi over 2 have an x value here. Right? These create a vertical line. Our x value is 0. You can't put that in the denominator. So this is undefined in both of those cases. So pi over 2, 3 pi over 2, undefined. Our 3 pi over 4 and 5 pi over 4 have opposite signs. So in the second and fourth quadrants, right, our x's and y's have opposite signs. So they're going to be a negative 1 for both of them. I did that wrong. No, fourth quadrant, that's that one. 7 pi over 4. 5 pi over 4 is third quadrant. Both are negative, so that divides out. Right, 3 pi over 4, 7 pi over 4, the signs are different. Therefore, negative. Okay, so then the other ones become a little bit harder, but it's not that hard to figure out, right? So pi over 6 is shallow. Okay, and then that also, pi over 6 had a 1 and a 2 and a root 3, or divide all of them by 2. This is just what sticks in my head all the time. We wanted y over x, so this is going to be 1 over root 3 for pi over 6. Or if you want root 3 over 3, that's fine too. That's also going to be the same for 7 pi over 6. And that should be it. Okay, and then pi on 3 is going to be our big angle here. Which is going to be our y over x, but in this case, right, it's oriented slightly differently. It's the tall one divided by the short one. So root 3 over 1 It was just root 3. So that's going to be here, and that's going to be at 4 pi over 3 as well. We're going to get root 3. Okay. 5 pi over 6 and 11 pi over 6. Again, they're shallow, but they're negative. And they have to have the same value overall as the other pi's on 6. So negative 1 over root 3. And 5 pi over 3 and 2 pi over 3, both are going to be negative again. And this time they're going to have big values. So this is going to be our root 3, negative root 3. Alright, so then what do we get for this one? Well, it's a bit different. Not like incredibly different, but... Alright, we get our 2 pi out here, we get our 0, we get our pi over 2, 3 pi over 2. These immediately, right? We know that these are going to be asymptotic, undefined. At 0, right? At 0 we get 0, at pi we get 0, and at 2 pi we get 0. And then we have 1 and negative 1 at all of our pi's on 4. So this one is positive 1, this one is a negative 1, this one's a positive 1, this one's a negative 1, and so on and so forth. Typically, I'm also going to just draw these in. Right, if we want to draw in the other ones, again, we're going to get a third of the way away from our pi's on 4. We're going to get one that's a fairly low value here. Again, 1 over root 3 or root 3 over 3. It's less than a half. Not sure exactly what the value is. It's fine. Don't worry about it. You can plug it into a calculator if you're really dying to know. But we're running out of time here. And then this is 2. Root 3 is 1.76, I think we discussed. Something like that. It's like, it's pretty close to 1.75. Right about there. And here, we get this behavior. All right, these are going to go through our x-axis at an angle, first of all. They are not like cubic functions. Again, just like we were talking about earlier, these are based fundamentally on circles rather than polynomials. Polynomials are these additive relationships. Circles, on the other hand, are limited. So you can't go outside of this amount. In this case, you can't go horizontally terribly far before the tangent function goes off to infinity. So they're bounded within a certain space. Whereas polynomials are all unbounded. They can go as far as they want. Okay. Waffle, or anybody else, got any more questions on this type of stuff? I would like to go over function transformation. Let's say next Tuesday, unless that's like really really late in terms of your semester. Might be able to pull a couple of extra sessions to get some, get some stuff figured out. I don't want to subject you all to more ads, so we're going to Oh, you still got a month or two. Okay, good. We're gonna see if we can roll out to somebody else who's doing math, question mark. That one's in Russian, so I don't think that's gonna help terribly. Maybe not. Alright. We're gonna go see Astro Canuck, who is an astrophotographer and astrophysicist living in Canada, and yeah, he's a good guy. His name's Tom. Does all sorts of fun stuff. Right now he's putting together some giant Legos. So we will be back tomorrow for our next differential equations class. We're going to be dealing with more applications, and I'm going to try to see if, like, how far we're going to take that. And I will be back apart from that whenever I feel like it, / Friday. Friday is going to be our typical game session, and could have, yeah, we could do some other stuff. We'll figure it out. I don't know. And then again, Monday, Wednesday for differential equations class until it's done, and Tuesday for miscellaneous math type stuff. I will also see you in any of the other Math Chads chats. And so if anybody has any particular want to go see them, please feel free. I will have a good week.